Introduction to Mathematical Proofs playlist, we'll be talking about the pigeonhole principle, an incredibly intuitive idea that helps us solve many types of problems. The idea is this: if we have 9 boxes and 10 pigeons, and we have to map the pigeons to all the boxes, then we can guarantee that at least one of the boxes have 2 pigeons. For example, if 9 pigeons decide to take their own box, we'll always have one pigeon that's just chilling, and it'll have to go to one of the other 2 boxes. And that's it. That's the pigeonhole principle. That's literally it. Interesting thing here, it shows that there's a connection between size and the possibility of bijections between sets. For example, we can never form a bijection between a set with 9 elements and a set with 10 elements because we will never have an injective function. Now let's go back to the diagram. Here we're assuming that it's a surjective function. It doesn't have to be a surjective function. It could be the case that one box has 3 pigeons or 2 boxes have 2 pigeons, but we're thinking about the worst case. In the worst case, the only thing we can guarantee is that at least one of the boxes has 2 pigeons. So in the pigeonhole principle, we don't necessarily have to assume that there's a surjection. We're just showing that there can't be an injection. Yes, we can have bijections between sets. Let A and B be sets. Then if there's any function from A to B such that that function is a bijection, or it's a bijective function, then we say that there's a bijection between A and B, or that A and B are bijective. So we extended the idea of a bijection from a function to a set just by using the sets as our domain and codomain for our function. And likewise, we can say that A and B are injective or surjective when F from A to B is injective or surjective respectively. How do we represent size of a set? Well, in this case, we use the absolute value symbols, or the 2 lines on the left and the right, and then we'll just, give it a number. So for example, if it has elements 1, 2, and 4, then the cardinality of A is 3. Yes, we use the word cardinality. The reason why we use the word cardinality and not size, we'll talk about in the next video. Let's relate this idea of the pigeonhole principle and cardinality. So if A is a set with 5 elements and B is a set with 4 elements, then by the pigeonhole principle, we can't have an injective function from A to B. Think about it. If you have 1 to A, 2 to B, 3 to C, 4 to D, where does 5 go? It'll have to go into one of the places. We don't know where it's going to go. We know that one of the elements in B is going to be mapped to twice. There cannot be an injective function. And in this case, we'll notice that the size of A, or the cardinality of A, is greater than the cardinality of B. Now we'll consider a function from B to A. Well, if we go backwards, this is kind of the opposite of the pigeonhole principle. If we have 4 pigeons and 5 boxes, we can't put 1 pigeon in every box. So in this case, such a function can never be surjective. Now we're abstractifying away from the sets themselves and more about the cardinality of the sets. We'll notice that if the cardinality of A is less than or equal to the cardinality of B, then we can find an injective function from A to B. Now we can think about this from the pigeonhole perspective. Let's say that the cardinality of B is 5. Well, if you have one element in A, you can map it injectively 2 elements, map it injectively 3 elements, map it injectively 4 elements, map it injectively 5. You can still map it injectively. But the second you get to 6, when it becomes greater, then you can't map it injectively. Then we have to apply the pigeonhole principle and be like, well, this doesn't work. So that's why if the cardinality of A is less than or equal to cardinality of B, we can find an injective function. Likewise, we can do the exact same thing, but for surjections instead. If the cardinality of A is greater than or equal to the cardinality of B, we can find a surjective function from A to B. Remember, this is the second case, the opposite of the pigeonhole principle. If you have 6 pigeons and 5 pigeonholes or 5 boxes, well, yeah, you can make it surjective. If you have 5, you can make it surjective. But if you have it 4, you can't make it surjective anymore. It's literally impossible. And then we'll notice something very interesting. When can we have an injective function and a surjective function? When the cardinality of A and B are equivalent or equal. Only in that case can we find a bijection from A to B and backwards in the exact same way. And indeed, this logic works backwards as well. Think about it. If we can find a bijection from A to B, we can match up elements 1 to 1 in a unique way, so they must have the same cardinality. But then we can also reverse this backwards. If we can match elements up 1 to 1 in a unique way, and indeed this logic works backwards as well. If we can find a bijection between A and B, we can definitely match up the elements 1 to 1, right? Because we're showing that it's injective and surjective, so then they must have the same cardinality. They must have the same air quotes size. So that's enough to talk about the cardinality. Let's talk about 2 cool consequences of the pigeonhole principle. I claim that I can come up with a program that'll take any file that you have and decompress it by 5%. And then I have a decompression algorithm that'll decompress the compressed file back to its original size. So I claim that I can decompress everything by 5% and take it back. Does such a program exist? The way we're going to do this is assume for the sake of contradiction that such a program does exist. Then consider the set of all files of size 100 and x, and we're going to call this set or denote it with capital D. The size 100x doesn't really matter. You could use x itself, but 100x is really nice to work with because 100% to 95%. And there are 2 to the power of 100x many possible files of this size. To understand why this is the case, well, you have to understand how files are stored. Files are stored in binary form. So that means that every bit is a 0 or a 1. That's what a bit is. A byte is 8 bits. So kilobyte is 1,000 bytes. Now, let's think about this. If we have a file with 1 bit, it's either a 0 or a 1, since the 1 bit is 0 or 1. So there's 2 to the power of 1 many files of the size if we're using bits as our unit of size. But then if we have 2 bits, well, the first bit can be 0 or 1 and the second bit can be 0 or 1. And notice that they're independent of each other, so we have to multiply the options together. We can either get 0 0, 1 0, 0 1, or 1 1. We have 4 options. That's 2 to the power of 2. Then if you have 3 bits, well, you have to multiply by 2 again because the third bit's independent from all the other ones. The choice of third bit doesn't depend on the other 2 bits. So that's 2 to the power of 3, which is 8. And you can keep doing this over and over. So if you have 100x many bits, there are 2 to the power of 100x many possible files of this size. After compression, the files are now of size 95 to the x. There are 2 to the power of 95x many possible files of the size, and we'll denote this set with C. Now, our contradiction. Our decompression algorithm can't uniquely map all the compressed files to the decompressed files. Let's think about it. The size of all the compressed files is 2 to the power of 95x, which is less than the size of the decompressed files or the regular files, 2 to the power of 100x. So we have that the cardinality of C is less than the cardinality of D, so we can't find a surjection from C to D. So this is kind of the opposite of the pigeonhole principle. Oh, we can't find a surjection. But if you wanted to think of a function that goes from the decompressed files or the regular files to the compressed files, what we'll find is that 2 uncompressed files must go to this one decompressed file. Then how would our decompression algorithm reverse that step? It can't uniquely reverse that step. It's not possible. We can't have an invertible function. Thus, our decompression algorithm can't exist. So such a compression machine can't exist at all. And here's another cool one that I like. Consider the following numbers: 647, 647 squared, 647 cubed, all the way to 647 to the power of 11. Without any calculation, what can we say about the last digits of these numbers? Well, there are 10 possible last digits and 11 possible numbers. Well then, what that means is that at least 2 of these numbers will share their last digit. At least. This is the lowest bound we can come up with. We don't know which numbers and we don't know which digits, but we know that there is some bound. There is some limit. And while the actual lower bound is much stricter, we have some conditions. We finally have some conditions that we can put on this. We know for a fact that 2 of them will share their last digit. PHP is really good at finding elementary or primitive bounds or limits. I mean, yeah, you might be like, okay, what's the point of having these? Well, we can prove that they exist. You can prove them, right? It's not like I think that this is the limit. No, you can mathematically prove without a shadow of a doubt, this is a limit that I found. Okay. And one cool closing remark, PHP is kind of like the first step into a topic of mathematics called combinatorics. Combinatorics is the math of counting things, counting combinations, way that you can combine things and stuff like that. Okay, that'll be all for this one. I'll see you later. Bye.